Okay, I can start. Let me introduce GPRS PCU implementation for OpenBTS. PCU it is a package control unit. Really, it's not only PCU implementation but also channel codec unit implementation too. But it doesn't matter. First, I will briefly review GPRS technology and several important GPRS features, and I think I will finish with some comments about our implementation.
And then we will have discussion.
Yes. Okay, and let me start with a short introduction to GPRS architecture. You can see traditional GSM architecture, but GPRS requires some extensions of GSM architecture by adding several elements such as CCU, it's a channel codec unit, PCU, it's packet control unit, and GPRS core network, which consists of SGSN and GGSN. You can see these elements in green frames. And SGSN is serving GPRS support node, and GGSN is gateway GPRS support node. Okay, now let me describe GPRS core network in details. It consists of SGSN and GGSN. SGSN, main tasks of SGSN are mobility management, control of network access, and ciphering and authentication. And GGSM provides just an interface to external packet data networks and some routing functions and firewall functions to protect the network from the unwanted data. And as you know, we already have open source implementation for SGSN and GGSN. For SGSN it is OsmoDevCon'12, and for GGSN it's Open GGSN. And but not all nodes of GPRS network have open source implementations. For example, CCU and PCU haven't it? So the main tasks of channel codec unit are channel coding, different schemes 1 until 4, and then it's forward error correction, interleaving, and measuring of different radio parameters, signal level and quality. And PCU packet control unit provides radio resource assignment, radio channel management, segmentation and reassembly of upper layer frames, and transfer of RLC blocks. So we should implement CCU and PCU to provide full open source GPRS network implementation. And the first question, it is the architecture of this implementation. In all the books and specifications, you can find 3 different cases for PCU position. As you see, it can be integrated in BTS, BSC, or SGSM, but for our implementation, we have something different. You can see the new picture where we have already Osmo SGSM and we have already OpenBTS. So we should implement packet control unit, and it should communicate with Osmo SGSM using GB interface, and it should communicate with OpenBTS. So we have
so the difference is that in OpenBTS we don't really have a BSC, so and it's really not in BTS because it could be separate. So it's a kind of mix of first and the second. And we don't have ABIS and we don't have BSC, so it's closer to the first one, but it's actually a separate executable, so it's not quite in BTS. I mean, it's kind of mix architecture.
Okay. So in the next slide, you can see GPRS transmission plane. It consists of layered protocol structures and interfaces. So protocols for SGSM and GGSM have already implemented, and for us, we should implement BSS part of protocols. There you can see GSM radio frequency, medium access control, radio link control, and BSSGP. It is BSS GPRS protocol and network service. And all these layers should be implemented in CCU or PCU. And of course, AR interface and GB interface too. Now, let me describe some main GPRS features. First of all, we can start with GPRS radio interface. GPRS physical layer is based on that of the GSM. It's not many differences. First of all, GPRS uses TDMA and uses normal burst for transport data units, and it's very important that GPRS uses JMSK modulation. So that is not much different from GSM. And when we should implement packet data channel, it is a physical channel which is used for packet logical channels. It has some differences from traditional GSM. It's dynamically allocated in the cell by the network, and it is mapped on 52 multi-frame. You can see 52 multi-frame structure for PDCH. It consists of 12 radio blocks. Each radio block consists of 4 normal bursts, and there are also 4 access bursts which used for PTCH channel and 2 idle frames. So in GPRS we have additional logical channels um, not not all of these channels are mandatory. Only PDTCH channel packet data transfer for packet data transfer and PACCH channel are mandatory, and the other channels can be implemented optionally because their functionality is the same as for traditional GSM channels.
So we could just reuse traditional channels for initial implementations. So packet channels, specific channels for GPRS are a little bit more efficient than using traditional channels. But for a simple implementation, we could go with using just the traditional GSM channels for control units, for access requests, and so on.
Especially on a single TRX cell. Because I think most of these are only used in larger multi-TRX cells, where your rash and whatever load on the CCCH of a classic GSM is already high, and you want to reduce the load on those, but a single cell.
And the next important feature that should be implemented, it is capacity on demand concept. You can see the picture time slots and timeline. In green, it's a packet switch channels, and the blue is the circuit switch channels. And resources for GPRS may be dynamically allocated depending on how many users require them, and how many channels resources are available at this moment. At the picture you can see that time slot number 7 is static allocated, and time slots 3, 4, and 5 are dynamically allocated and can be used for circuit switch channels and for packet switch channels.
Yes. So when you don't have a call on some time slot, you could allocate a packet data channel on this free time slot, if it's a dynamic allocation. And if it's a fixed allocation, then the whole time slot is dedicated to GPRS only. And what we've seen is that usually there is like a one dedicated time slot, and other time slots are allocated dynamically.
Okay. Now let me tell you about different allocation modes for the uplink direction. It's allocation of physical resources. Several mobile system may be multiplexed on the same PDCH channels, and the task is to share the uplink bandwidth between several MS mapped on the same PDCH, and there are 3 allocation schemes.
The problem we have here is that in a circuit switched mode, every circuit switched channel was used by a single mobile, and now a single packet data channel should be used by many mobiles. So many mobiles can access the same like time slot, and there was a solution for this, which is like a dynamic allocation scheme, or actually a fixed allocation scheme as well, but it's deprecated.
Yes, and fixed allocation deprecated, and usually used dynamic allocation, and some principles of dynamic allocation you can see in the next slide. For dynamic allocation, network uses USF, it's uplink stage flag. USF is used as a token which given by network to mobile station, and to allow transmission of the uplink block, and mobile phones just monitoring necessary USF, and when mobile phone receives necessary USF, it just send uplink radio block on the next block in the frame.
So yeah, the idea that there are, if I recall correctly, 8 USF is a 3-bit number, so there are 8 possible USFs. So at every given moment, 8 mobiles can transmit data on a time slot. And what happens is that when mobile phone requests to transmit data, base station allocate a USF, send this USF to mobile phone, and then mobile phone starts listening for this USF on a downlink. And when it sees USF allocated to this mobile phone on a downlink, starting from the same from the next frame, it starts transmitting in uplink. So that's how the multiple access is implemented. And then base station starts transmitting next USF, and next mobile starts transmitting the data. And USF is transmitted like as a first 3 or 4 bits of downlink, like normal burst, if I recall correctly.
Okay. Now, some words about RLC MAC layer. This layer has very important tasks, and one of the main tasks is segmentation and reassembly of LLC frames. You can see it, and when RLC MAC layer receive LLC frame from the upper layer, it just segmentation it into RLC blocks and added different block headers and block check sequences, and after that RLC MAC layer just sent blocks to the physical layer, where every block consists of 4 normal bursts, and
So basically, what is the purpose of this? Is you get like an IP packet. It may be of arbitrary size, but in your radio channel, you have these radio blocks which are 4 normal bursts. So they have fixed size. What does this do is it splits a packet, a big packet of arbitrary size, into chunks which could be transmitted in these radio blocks. That's basically the purpose of this layer, and also the purpose is to provide retransmission. But yeah, retransmission and backward error correction.
Here on the next slide, you can see different differences in block structures. RLC marked blocks have blocks for data transfer, for signaling, it's different, and for downlink and uplink, all these blocks have different structure for headers, and also control blocks have special structure, and it is also a task for RLC map layer to decode and encode control blocks and control messages. It's in the specs, it's CSN1 used for encoding control messages. It is okay. And on the next slide, it's a very important and complex task for RLC map layer. It is TBF management. You can see TBF, what is TBF? It's temporary block flow. You can see a scheme of uplink TBF. When mobile station, for example, for uplink TBF, it's when mobile station receive LLC PDU from the upper layer, it's initiate TBF establishment, just send to DSS control block, necessary control message, and after that DSS receive answer. This is the first step of TBF. It's TBF establishment. In real life, it's a different types of TBF establishment for uplink, downlink, and different implementations. And after that, mobile station just receives data blocks. It's RLC data block transfer part, and after that, when the all data blocks are received, BSS just release TBF. TBF always initiated by the reception of LLC, and in the downlink, when the downlink TBF, it's the same structure. And of course, it is can be acknowledged and unacknowledged mode for RLC data block transfer. So all these parts of TBF establishment, TBF data transfer, and TBF release consist of TBF. It's temporary block flow, and TBF management is not very simple. It's really consists of many tasks such as backward error correction, TFI management, TFI it is temporary flow identifier, which identify each TBF, and USF management too, and many others.
So TBF is basically like a transmission method for a packet, for an AP packet, which is then split into LLC. And so you have to multiplex this in PCU to monitor QoS and to ensure that the available bandwidth is enough to send all the data and so on. So that's why it's so complex, because you have a very limited radio resources, and like internet may stream to you with pretty high speeds.
Okay, now we can discuss our implementation. Here you can see features which were implemented. At the OpenBTS side, it's handling of BCCH, RCCH, and for GPRS support. And we have implemented 52 GPRS multi-frame, 2 additional logical channels, PDCH and PCCH, and now we implemented only coding scheme 1,
Which is basically the same as in
Yes.
GSM. So we don't actually implement it,
we just reuse.
reuse from existing OpenBTS.
And we implemented channel access control functions, including access request and runs. It is OpenBTS side, and for PCU side, for packet control unit, we implemented segmentation of LLC PDUs into LLC data blocks and reassembled it. Segmentation of RLC mark control message into RLC mark control blocks and coding and decoding it. Minimal this is GP implementation for communication with SGSM and for use GP interface. Also uplink to BF establishment on CCCH and downlink to BF establishment. Also release and release of uplink and downlink to BF. And there are, you can see features on which we are looking now. It's L1 interface between packet control unit and OpenBTS for communication, where we are implementing an interface such as an OsmoDevCon' project, the same principles. And now we're working on GPRS attach procedure. We have already received and sent first steps, but it's need more time for testing. And the next slide, you can see next steps which should be implemented. It's first of all to build management with multiply mobiles, because now we work only with one mobile.
So this simplifies USF management, for example. We just have one USF number.
Set one USF.
That's all.
So it is a set of steps. It's a backward error correction. It is PDCH shutdown function for uplink and downlink data transmission. It's a TFI management, dynamic allocation, it's USF management, contention resolution procedure because it is several mobiles, paging procedures, and improved GP protocol. So it will be interesting to discuss which other features should be implemented, and because it is only minimal set of features which should be implemented.
Yeah, probably how do we better, how to make sure that we are compatible with both OsmoBTS as well, so we should reuse the code.
So I think it's all.
Okay. Well, it may be interesting to illustrate for those who are not familiar with the code, which I think is the majority here, that how you have been doing the CSN1 integration, for example. I think you did mention that you have the Wireshark and those files. I think it may be interesting to say a couple of words about those.
Okay, for for this implementation, we use not a generic this compiler, but we use Wireshark implementation for it, for decoding, and we just add encoding for this implementation.
Yeah, so the idea is that we took decoding part from Wireshark and extended it to doing decoding part and extended it to do encoding. And the way they do it is that they manually convert from like CSN1 to macros, to C macros, and then there is some like C magic happening, which generates like structures and accessors for this CSN1 structures. So could you show the code how it looks like?
Maybe show one data type as CSN1
Yeah.
so everyone sees, and then the Wireshark version.
Yeah, so here you could see
For example, it is
TDF release message.
PDF release message consists of C macros.
So this is just a set of macros. So you see the begin, end, and all those fields described with those names, and even some parameters. And, could you show how you access this? How you read and write this?
We have this one string encoder. It's a huge function.
Just show how you use this. In real code, how do you decode and how do you encode those messages? Just how you use these functions.
These functions.
Yeah, so that's how it's used in the code.
The result is not used to it. Do you have a function where you access attributes after you have decoded it? Could you just
Yeah, how do you access data in those structs after you decode them?
Okay, we have structures. I can show you. Structures like this, and you can.
So those are generated, right? the structures. They are generated from those macros or from parsing the C source code.
No, I don't think so.
No?
No.
Somebody has to manually write all that?
Yeah.
Yeah.
Oh. I know, I have to write some.
That defeats the entire purpose of CSM1.
Yeah, the thing is, in my shark, if you want a nice dissection with everything explained nicely, you kind of have to do a lot of things manually anyway.
Yeah, but now you have to specify things manually twice. You have to specify it somewhere in these macros, and then you have to specify it again in a header file. So I would have expected at least one of the two could be auto-generated from the other. But now you have to enter
Too easy.
twice.
You just can't go there.
But maybe
Yeah, but the question is for what level of complexity? Because if I look at something like release 11 GPRS CSN1 spec, if you want to hand code all of that, including inter-radio access technology, handover, edge, and all that stuff, it's going to kill you.
Yeah, that's. We'll burn that bridge when it comes to it.
Because if you, I mean, I have been experimenting with some proprietary CSN1 compilers, and just to give you an idea, if you, so what they generate, basically all the nested data types. If you want to have a single function, you hand in your RSC MAC message, and you want to have it decode everything. I mean, not specifying any more type information, any more hints. Then the resulting data structure you get is about, I think, 280 kilobytes large structure. It's a structure with lots of nested other structures, and you end up somewhere 284 kilobytes of that. And I mean, I'm not using that to sort of say it's a bad idea to generate the code, but I'm just saying that, I mean, to illustrate the complexity of the data structures that you're dealing with. And I think, I mean, yes, that particular tool costs like €2,000, but the generated code and the runtime library can be used from open source software. And I think for €2,000, if you want to write all that stuff manually and debugging and have all the bugs fixed that you have made by manually transcribing it, I think.
Send the specs to China and see if they can write the code.
Then
you have to check it. I mean, it's
yeah, but I think the idea is that pretty lot of this code is already like transcribed. I mean, so
yeah,
that's why we started doing this Wireshark, because pretty a lot of things are already here.
yes.
I'm not sure about how complete is that.
No, it's very complete.
The question is how many bugs did they make in manually transcribing it? Because, I mean, if I look at other dissectors of Wireshark, especially in the GSM field, there are bugs all over the place in decoding stuff.
Yeah, so actually Ivan is doing some unit testing for this. So he has been writing some unit testing code so that we could ensure that they're indeed correct.
I mean, sort of what I'm trying to say here is just that, given the sort of limited investment, is it really worth pursuing the route using manually transcribed messages, considering the probability of a reasonable amount of errors and mistakes having been made in there, versus maybe at some later point switching to an auto-generated format and then having to touch every single line of the code because all the data structures will look different, and all every field that you dereference in the structure will have a different, maybe different capitalization or something like that. So the transitioning later, I think, is an option that simply doesn't exist anymore.
But it could maybe be done with Coccinelle.
What?
Coccinelle. The semantic patching stuff that is used for the kernel.
What do you want to do with that again?
It could be used to do some rework of existing code to something new.
But it starts with things like, how do you allocate those structures? Are they statically allocated? Are they dynamically allocated? Who owns that? Is it freed? Does your encoder free or whatever? So I think transitioning between different CSN1 generated, either manually or automatic generated data structures is a major effort, if not only because of the sheer quantity of structures and objects and things you deal with. It's, I mean, just the number of messages, let me just see if I can quickly,
Yes, rather, I think 1,000 of them.
yeah, so if you just look at the number of information elements and structures in there, it's really, I don't know how I can quickly...
The email from you, where you calculated the size, I think it also contained number of messages. Well, I think at least there are several hundred of them.
I'm not really convinced that the guy who wrote the schematic didn't use some kind of tool to generate the base of the file.
It may be possible. But then also the question is, let's check what kind of release did they use.
Yeah.
Let me see if I can quickly find that.
Yes, but actually what I like this manual way is that you could fix bugs. I mean, if you know there is a bug in the standard, you could just easily fix it by hands and don't have to regenerate everything.
Yeah, but the regeneration could be as simple as having a git post-commit hook. And every time you update your CSN1 file and commit it to the repository will regenerate the code and add it to your commit message. I mean, we're talking about Linux command line tools that are shipped by this company, so it's not an unreasonable thing to implement without much.
Yeah, so yeah, actually it's goes down to question how many bugs is there and how complete is it right now. So do you know how complete is it? This Wireshark so
It's difficult to understand.
okay.
I know that encoder and decoder is work manually.
So probably if we have some.
We just need to find necessary message and to fix it. And it seems not difficult.
Yeah, I mean, of course, I'm not, anyone can do whatever he wants. It's a free world. Just have some question marks now. I mean, I don't, we don't have enough, enough interest in GPRS at this point that we at SysmoCom have actually started any implementation. Or, I mean, we would love to, but simply not the kind of business that rectifies the amount of investment. But if I was to start, I would seriously consider code generation rather than depending on something where you don't. I mean, maybe it would be worth to try to speak at least to whoever generated that Wireshark code and find out what version of the spec they used and whether it was done automatically or
Yeah, maybe.
I mean, writing. I quickly, I mean, since I didn't know much about CSN1, I investigated that, and I think writing some code generation ourselves is out of the question. It's just too much work.
Yeah, I mean, there's a website dedicated to CSN1 that has a section named like CSN1 bugs or something like that, where it's basically say that it's an ill-defined standard and there are things which are not defined, which you can't get from the notion. I mean, from the description, unless you know what they exactly mean. So
yes, well, that's a different problem. But I mean, I think the primary problem is that you have back references and that kind of stuff. So it's not just that you have to parse the CSN1 syntax and somehow generate code, but in CSN1 you have like 5 elements in a structure, and the 5th element can have like a length that depends on something else that happened or a certain value 3 elements before in that structure, and those kind of constructs I think is what really makes it hard to do so. And there are other very powerful syntactic constructs that they use, and so I think that's unrealistic to
yeah, so let's, yeah, I'm just looking into this website that has a page named Pitfalls, and it basically says that, however, due to difficulty of writing the encoding with such a language, the 3 GPP definitions are often wrong, and it has some list of
yes.
pitfalls.
I've fixed all those. So using the evaluation version of such a commercial tool, I went through all the syntax errors in the official 3GPP specs, and there is a Git repository on Git Osmo.org where all these syntax mistakes have been corrected.
For GPRS CSN1.
For GPRS CSN1 source structure.
Okay.
So there is a file that, at least according to 2 different commercial tools now, is syntactically correct and generates output. So that's, yeah, I think it was about 200 bucks, but not, how can I say, not incredibly complex things, just like capitalization mistakes or a colon missing or some bracket missing or some stuff like that. It was not all that much of a one of the funny things was one of the bugs actually caused the CSN1 compiler to run out of memory. It was 7 gigs of RAM, 7.5 gigs of RAM.
Yeah, so you have those files already checked in somewhere.
Yes, they are on the Osmo Code Git repository since early December.
You could probably post this to our other part. Okay, it doesn't work.
That is offline.
Okay. You could probably do this later.
Yeah. And also the fixes have been committed as separate changes, so you can actually, of course, review the Git history and see what kind of changes were made to the original files. Yeah. Okay. Anyway, I don't want to talk more about that code generation now.
Yes, I think the interesting question is how do we interconnect with OsmoBTS as well as.
I think that shouldn't be all that difficult, because fundamentally all that you need is a couple of primitives for sending and receiving bursts or Mac blocks, whatever it is, to the layer 1. And our layer 1 has, you can just state what kind of coding scheme you want and then the data payload, and you have to, at which point of time it has to be sent. It's in our case, it's real time, so layer 1 with some, with some advanced timing, the layer 1 will tell you there's a ready to send indication on this particular time slot at that particular GSM time, and then you have to return some data, you have to feed some data inside. What is it exactly, what type of burst and so on you want to send at that particular timing. Mm-hmm. And for that can be seen from the OsmoBTS code. It's the same for circuit switch as for GPRS. And for receiving, you will get pH data indications, which again the same. You have a small header that will tell you in which coding scheme it was, what frame number it was, what time slot it was, and so on. And it will then have a buffer where the actual payload is in. So I think
that's how you get it.
Yes.
So that I think that should not be horribly complicated. What's going to be more interesting is once you actually want to do this dynamic dynamic allocation, where you need to know which kind of physical channels are used by circuits and services, which is sort of, well, we have that information, but I think generally that the BSc has a much better idea of that kind of information, of course, in a more classic environment. But it's still possible in the BTS. So yes, once that kind of once you need that kind of information, we need to see how to define a common interface to access that.
If I understand correctly, right now we are not going to implement this dynamic allocation like right now because we have other issues. Yeah, but we're definitely looking into how to do this.
Yeah.
Because
But
for OpenBTS it's a little bit different because it's all inside.
Yeah, but since your PCU is an external process, you also need some kind of interface.
Yeah, it's over BGP.
Yeah, but okay, then the question is just to settle on an interface that can be implemented on both OsmoBTS as well as OpenBSC, OpenBTS.
We could probably just look into some definition of the interface if you want.
You mean the interface to the layer 1?
Yeah.
Yeah.
Or
Alexander, the OpenBTS -GPRS on code.google.com is not
what?
There is a OpenBTS -GPRS on code.google.com. That's not your.
What? On Google Code?
On Google Code, there's
No. We are on GitHub. It's under my login on GitHub. GitHub/chimeris/OpenBTS something.
Okay, no, it's in the branch.
I think on the Google Code it was someone just cloned our GPRS work for experimenting.
I think, I mean, just
actually we are running out of time, I think, so we could probably, it's 5. Yeah, it's coffee break right now, so.
oh, but since there's no coffee.
Yeah, so we probably could just have a private conversation.
Okay, I just looked at the code a bit during the talk. But yes, okay. Then we officially start the break and we continue to talk about the